Assalamualaikum. So this is our lecture 7. So in this lecture we'll be discussing about the null space of matrix A. But before that we want to have some recaps from the previous lecture, which is lecture 6, and it was about the vector spaces and subspaces. Okay, so recap of lecture 6. So in lecture 6 we started to study our main concept with the vectors, which is vector space, and the requirement to be a vector space was, so vector space requirements were, so the condition was like all combination of CV plus DW, which is the linear combination, would be inside the vector space where this V and W are any vectors in the space. And there is another condition or another requirement, that is, which is actually a part of the first requirement, which is the origin should be, the origin should be inside the vector space. So these are the two main conditions of vector space. Okay, and we also talked about a subspace. So a subspace is basically a subset of a vector space. So it was a space inside a vector space. So could you remember all the subspaces of R3? So we discussed it in our last lecture, that a plane through the origin in R3 would be a subspace, a line through the origin in R3 is a subspace, and the whole system, the whole 3D coordinate system, is also a subspace of R3. Okay. Suppose you have two subspaces, which is P and L. Okay, so this, let's say this P is plane through the origin in R3, and this L is basically a line through the origin in R3. Okay. So if I try to draw it, it's difficult to draw a plane in R3 on a 2D surface, but let's try. Let's say this is our plane, This is a subspace in R3, and let's say this is a line. So this is also a subspace in R3. So can you tell me, is P union L a subspace? So P union L a subspace or not? So P union L means all the vectors in this plane and all the vectors in this straight line. So the answer is no, because there, if I take one vector from this, straight line and one vector from this plane, let's say, okay, so their addition, and if I add those two vectors, it is very likely that their addition will not be inside this plane or in this straight line. So in that case, it would be somewhere else. So in that case, it would not be a subspace. Okay. This P union L is not a subspace, because any linear combination from the two vector spaces might not be inside that same vector space, which is the P union L. So that means that violates the very first rule, the very first requirement, which is this one. Alright. So this is not, so P union L is not a subspace. So the second question is P intersection L a subspace? So what is the common element between these two subspaces? The answer is the origin, right? And we all know that this is the origin. The origin is the common element between these two subspaces, and we all know that the intersection point, which is the origin, is definitely a subspace, because any linear combination, 0 origin plus origin is equals to origin, and any scaling, like multiplying this origin with any scaling factor c, would also be resulted in inside the origin. Alright. So that fulfills the two requirements, and we have the origin as a vector space. Sorry for the interruption. So that was basically it. So this was the discussion of two subspaces intersecting in R3. Okay. So let's go to the next section, which is the discussion on the column space. So I already discussed started the topic column space in the previous lecture. So I'll be just discussing some key points here. Column space of A. So A is any matrix here. So let's say we have an example matrix that is, let's say 1 2 3 4 1 1 1 1, and then let's say 2 3 4 5. Okay. So the column space of A, of matrix A, is a subspace in R4, because if you look at the columns, there are 4 elements here. So that belongs to the R4 dimension. Okay. So the column space of A is subspace is a subspace of R4, right? So this column space here is, as discussed in the previous lecture, is the all linear combinations. So column space is the space that is created by the columns. Okay, so this is basically all linear combinations of the columns. So my question here is, I asked this question in the previous discussion class, that if we have this equation Ax equals to b, that means this matrix 1 2 3 4 1 1 1 1 2 3 4 5 into x1 x2 x3, three unknowns, and we have a solution set, let's say b, and there are 4 elements there, so b1 b2 b3 b4. So my question is, for which b's I can solve this x. This is my question. So the answer is, there might be different b's here. So one example of b's can be 0 0 0 0. So if we have all zeros at the b as b, then we can definitely solve this by putting all the values of the unknowns as zeros. Okay, now which other b's we can solve? So one example solution can be so one example solution can be b equals to 1 2 3 4. We can have this b. How? If we have the solution set 1 0 0. How is this possible? Because we are taking ones of the first column, which is this one, and none of the other columns. So none of the other columns are taken, and ones of the first column is taken. So that gives us the solution for b. There can be another solution. Let's say b equals to, we have, let's say 2 3 4 5. So this is also solvable, because if we have x equals to 0 0 1, that means we have taken none of the first column, none of the second column, and ones of the third column, none of this one, none of this one, and ones of this one. Then we can achieve this solution b. Okay, so we can reach this combination as well. So as you can see here, depending on the combination of the columns, we can achieve different b's. So that line that I just said is very important here. The different combinations of columns can be achieved by this b, right? That means, then what is the different combinations of the columns? That is basically the column space. So if we have any solution b that is inside the column space of A, then only in that case we can achieve that solution. If we have any if we take any vector or any solution that is not inside the column space, let's say one example can be minus 0.5, 1 by 3, 0, and minus, let's say, 7 by 8. So this solution here is, I think, cannot be achieved by these columns, as this is not in the column space of A. Alright, so I can solve Ax equals to B. So I want to write that line here. I can solve Ax equals to B exactly when my B is in the column space of A, which is the C of A. Okay, so that's why we are very much interested in the column space, because a column space actually describes if we can achieve a solution or not, if we can achieve a particular vector or not. So I have another question, and that is do all the columns contribute something new to the column space? Do all the columns contribute something new to the column space? So if we again take that matrix back, 1 2 3 4 1 1 1 1 and 2 3 4 5, you can see that the third column is basically, so the third column 3 is basically the linear combination of the first and the second column. Alright, so column 3 is not adding anything new to the column space. So the column space described by column 1 and column 2 is same when column 3 is added with the column space. So you can definitely throw away column 3, or you can definitely throw away column 1 if we take only these two columns, or we can also throw away column 2 if we take the first and the third column. Okay. So any dependent column can be thrown away when we talk about the column space. Okay. So I think this part is clear. So now we'll be starting our main topic of today, which is the null space of A. Okay. So we'll be starting today is the null space of A. So the null space of matrix A is basically all solutions X where we can get Ax equals to 0. So let's write that down. So the null space of A which is a matrix, is all solutions X for which Ax equals to 0. Alright. So in the previous example we had A equals to 1 2 3 4 1 1 1 1 and then 2 3 4 5, and let's say we want to find the null space of A. So in that case we have 1 2 3 4 1 1 1 1 2 3 4 5 multiplied by the vector of unknowns, which is x1 x2 and x3, and at the right hand side you have to solve 0, right? So let's solve this solution X. Okay, so in this case the null space is a subspace of R3. The null space for this guy, this matrix here, the null space the null space is a subspace of R3, the subspace of R3. Why is that? Because as you can see that the solution here will have 3 elements, okay, and that contributes to the 3 dimension of R3. So without looking at, so we have to solve this equation, okay. So without looking at the equation, you can tell me one solution, and that one solution is x equals to the origin. So for all matrix, whether it is dependent or independent, the one solution for the null space is the origin. There might be other solutions, but there has to be one solution for the null space, and that is the origin or the zero matrix, okay. Now can you tell me another solution for this matrix, or for this x equals to 0 equation, which is this? So I can tell you one solution, that is, let's say x1, and that is positive 1, and negative 1. How did I take it? I could take it because, as you can see, that the third column is basically the linear combination or the addition of the first and the second column. So if I add these 2 columns, and if I subtract the third column from it, then I can definitely get a 0. All right, so if I write it down, 1 2 3 4 1 1 1 1 and 2 3 4 5, as you can see, if I multiply with 1 1 and a negative 1, then I will get definitely a 0 here. Alright, so this is one solution. So can you give me another solution? Yes, another solution can be given, that is 2 2 and negative 2. Alright, another solution can be given, the 3 3 negative 3. In fact, I can write all the solutions in a simple vector form, and that vector form is can be derived from here, and that is c into 1 1 negative 1. And this is so beautiful that even the origin is inside here. If the c has the value 0, then you will get all zeros, or the origin from here. So can I tell this guy a subspace? So let's draw it down. So this is R3. So so the vector is 1 1 negative 1. So let's say this is x, this is y, this is z. So let's say this is 1, and let's say this matrix 1 1 and a negative 1, and all the linear combinations, that means it is multiplied by a factor of c, so it is stretched in the opposite direction and in the forward direction. So this is the whole line, c into 1 1 negative 1. So this whole line is definitely a line in R3 which goes through the origin, which is definitely a subspace. So this null space that we've just found out here is a subspace in R3. So now why we're calling it a space? Because like the solution, every time the solution of Ax equals to 0 will give you a subspace in any particular coordinate system. All right, so in this case this is C into 1 1 and a negative 1. So this is the null space of this particular matrix A. If we say it in a reversed manner, it would be like if AV equals to 0 and AW equals to 0, then obviously sorry, there's a spelling mistake there. Obviously A into V plus W equals to 0 and A into CV or A equals to 0 or into CW equals to 0. So this is true for all the subspaces, sorry, all the null spaces or all the solutions of a null space of A. Okay, so this is a very special case because you'll only get a subspace for B equals to 0 0 0 0. For any other solution, like let's say for 1 2 3 4, you cannot get a whole subspace for this solution, but you can get a whole subspace for this B equals to 0, but you cannot get a whole subspace for B equals to 1 2 3 4. Alright, because one solution was for this, one solution for this B was 1 0 0, as we saw in the previous example. Another solution can be, you can check by going backward. Another solution can be 0 negative 1 and 1. Now if we try to add or multiply with a scalar, it goes out of the claimed vector space. Okay, but for 0 0 0 0, the solution always stays in the same vector space. That is why it is called a null space, a subspace in any particular vector space. Okay, so if you're not convinced that why you cannot get a vector space here, so just think from the perspective of origin. The origin is not included here, right? The origin is not included in the solution set of 1 2 3 4. So that is why it is not a vector space or vector subspace. All right, and for any other, you can check, like you can take any A, take a rectangular matrix, all right, and you can check that the solution set for Ax equals to 0 will always give you a subspace or a vector space itself, which is called the null space. Okay, so I told you to find out for the rectangular cases, because for independent 3 by 3 matrix or 4 by 4 matrix, the null space is only the 0 vector, C is 0 0 0, because as the matrix is independent, so that means you cannot get any other combination of the columns that will give you that will result in a 0 vector. All right, because all the columns are independent in case of independent vector, which determinant is not 0 in case of invertible matrices or non-singular matrices. So you can check this fact by taking rectangular matrices. So the question is, how do we find the null space? How do we find any null space, the null space of any vector, or sorry, any matrix? So the method of finding the null space. So the method of finding the null space is pretty simple. We learned how to find out the solution for any matrix, and we learned a method called the elimination, Gauss-Jordan elimination, and we can simply adopt that solution method. Okay, so let's take one matrix A equals to, let's say, 1 2 2 2, then 2 4 6 8, and then let's say 3 6 8 10. So this is our matrix, and our solution is B equals to definitely 0 0 0. Alright, so let's take the augmented matrix here. So 1 2 2 2, 2 4 6 8, 3 6 8 10. So this is the augmented matrix. So now we have to find the pivots, right? So what we can do is that we have to make this position and this position zeros. Okay. So we can do it by multiplying the first row by 2 and then subtract it from the second row, and let's do it together. And in case of R3, what we can do is that we can subtract 3 multiplied by the first row from the third row. So from this we can get 1 2 2 2 0 0 2 4 0 0 2 4. So this is one pivot here, and this is another pivot here. You can also get the zeros under the pivots. So this is another position where we should get 0. So you can simply get it by subtracting the second row from the third row. So it should be 1 2 2 2 0 0 2 4 and 0 0 0 0. So by this we got a very special staircase form of this upper triangular matrix. So you can see that it has a significant structure, and this structure is called the echelon form. This is called the echelon form. Okay, that means this staircase format is called the echelon form. So from this matrix you can see the rank is 2. So the rank is basically the number of pivots in any matrix. After the elimination you can check it, the number of pivots. Okay. So for this matrix, how many pivot columns or free columns are there? So free column means the columns where we do not have any pivot. Okay, so this echelon, so the matrix from the echelon form is basically 1 2 2 2 0 0, then 2 4, and then all zeros. So we have two pivots, it is this one and this one. So these are called the first and the third columns are basically the pivot columns. These are the pivot columns because it has pivots, they have pivots. Okay, and these two columns, this one and this one, these are free columns. Okay, because they're free of pivots, these are free columns. Alright, so why are they named free column? Because we can assign any value to these unknowns freely. Because one thing you can check or you can notice that I simply discarded this column here from the augmented matrix, because if you multiply any number with this first column and subtract it from the second column, or multiply any number from any of the multiply any number in any of the rows of zeros and then subtract it from any other column, you will get eventually 0. So that's why I did not augmented that column here. Okay, so from this we can have 3 or 2, let's write down 2 equations. Okay, so the first equation is from this row, that is 2 into x3 plus 4 into x4 is equals to 0, because you have all zeros at the right hand side. Okay, and from the first row we have x1 plus 2x2 plus 2x3 plus 2x4 equals to 0. Okay, and we have 2 free columns, as I said, that we have, these are the free columns. Okay, and you can also write down this 0 into x1 plus 0 into x2 if you for clear understanding. Okay, now when we have free columns, how to solve them? So the convention, so as I said, the free columns are named free columns because we can assign any value to these unknowns freely. But for the convention is we have to assign 0 and 1s to the free columns while evaluating those unknowns. Okay, so let's say for this equation we have x2 equals to 1 and x4 equals to 0. Okay, so if we have x4 equals to 0, then we have x3 equals to 0 as well. Okay, and we have x2 equals to 1. So if we have x3 equals to 0, x4 equals to 0, x2 equals to 1, then from the first equation we get x1 equals to minus 2. So this is our one solution. So x could be x equals to minus 2 1 0 0, but from you saw from the previous example that any multiple of this equation or any multiple of this solution is a solution itself also. So you can multiply with any multiple any scaling factor c, and this would be the one solution. This would be one solution from the null space as well. Now, is this the only solution? The answer is no. First we saw for x2 equals to 1 and x4 equals to 0. Now we can find the solution for x4 equals to 1 and x2 equals to 0. Okay. Now just switch these values into these equations. So if we have x4 equals to 1, then from this equation we have x3 equals to minus 2. Then we saw that we assumed x2 equals to 0, and if x2 equals to 0, if we switch all these three values here in equation 1, we get x1 equals to 2. Okay, so this is our another solution, x equals to d, or x equals to 1 minus 2 0 2, and we already know that any multiple of this solution is a solution itself, so we can multiply with d. Now, is there another solution? The answer is no. Why? Because we can get as many solutions as the free columns. Okay, so if we have 2 free columns, we should stop after getting 2 solutions. If we have hundreds, or say if we have 1 free column, we have to stop after getting the first solution. Okay, so the null space, so this is one vector from the null space, this is one vector from the null space, and any linear combination of these 2 vectors is also inside that null space. Okay, because this is the first requirement to be a vector space, that any linear combination of a vector space should be inside that vector space as well. So the null space would be, so the null space of A is basically the linear combination of these 2 solutions. So these are called spatial solutions. So these are called spatial solutions, or these ones are called spatial solution. So we will see a lot of use of these terms, spatial solutions, in the next lectures as well. So this is the null space of a matrix A. Okay. So as I said, so there is one spatial solution for every free variable. Okay, there is, for each free variable you have one spatial solution. So how many free variables are there? So the number of free variables, so the number of free variables is n minus r. So n is basically the number of columns and r is the rank. Okay. So in this case there are 4 columns and the rank of the matrix was 2, so the number of free variables is 2. Right. Now I'd like to take one more step. So we got our echelon form. So our echelon form was 1 2 2 2, then it was 2 4, and all the other entries were 0. So this is our upper triangular matrix, or some upper rectangular matrix you can say, not a very upper triangular. So from this u we solved ux. From this u we solved ux equals to 0, right? So from this I want to get r. So r is basically reduced row echelon form. Okay. So before that I have one question. So you can see that the third row here is full of zeros, right? So why there are all zeros on row 3? Because you can see that in the very first matrix that row 3 is basically the combination of row 1 and row 2, this one and this one. So this is, if you add these two rows you will get the third row, and after the elimination process you discover that row 3 is a combination of row 1 and row 2. So after every elimination process, if there is a dependent column, you will see that it becomes all zeros. Okay, so now to get the row echelon form, so I have to, so the upper triangle, in case of upper triangular matrix we get we try to get zeros below the pivots, right? So in case of r we will get zeros above and below the pivots. Okay, so from this matrix I 1 2 2 2 2 4, if I from row 1 if I subtract, so I want to get 0 in this position. So how can I get it? I have to subtract the pivot from it, right? So row 1 minus row 2, so you will get 1 2 0 negative 2 0 0 2 4 and 0 0 0 0. So you can take another step and get this pivot as 1. So it can be r2 is r2 divided by 2. So 1 2 0 minus 2 0 0 1 2 and then 0 0 0 0. Now it is even easier to solve rx equals to 0 after this step. So in MATLAB you can immediately get this r. In MATLAB you can immediately get this r from the command r reference of A, reduced row echelon form of A. Okay, so if you closely look at the R matrix, you will see that it has a very interesting structure. That is, these are the pivot columns, right? So if you write down the pivot columns, you will see that 1 0 0 0 1 0. So it has a very similar structure. So these are the pivot columns. So it has a very similar structure with the identity matrix, 3 by 3 identity matrix. And here are the free columns, 2 0 0 and minus 2 2 0. So these are the free columns. So if we try to write down these pivot columns and free columns together, you will see that this particular portion has a very similar structure of I, and let's call this structure F, and we have all zeros at the bottom, so all zeros there. So it has this very distinctive structure. Alright, so there is one issue here, that we used two free columns here and we got two special solutions. Okay, so if we have only one free column, what should we do? So what we have to do is that we have to assume the free column as 1. So in cases of x2 and x4, we assume 1 and 0 for two different cases of spatial solution, but in case of only one free column, there will be one spatial solution, and in that case you have to assume the free column as 1. Alright, so if you take 0, you will get all zeros. That is automatically included in that null space. So this is the method of getting the null space of any matrix. So we'll be discussing on this null space in the next class, inshallah. So please follow the book for more exercises, because it is not possible for me to discuss about all the different exercise problems in classes, right? So, or in lectures. So please try to do some exercises from the book chapters as well. Okay, so thank you, and I'll see you in the next class, inshallah. Assalamu alaikum.